Waves. What is a wave? And by that, I don't mean the waves you see when you go to the beach. I'm talking things like light waves or sound waves. Well, a wave is an oscillation or vibration that could transfer energy without transferring matter. There are two types of waves, which are transverse waves and longitudinal waves. The difference between both these types of waves is that transverse waves are perpendicular to the direction of wave travel, whilst longitudinal waves are parallel to the direction of wave travel. Examples of longitudinal waves are sound waves or ultrasound waves. Now let's look at this wave. The top part of the wave you see here is called the crest, and the bottom part of the wave is known as the trough. The amplitude is half the distance between the crest and the trough. Now, the wavelength is the distance between one wave to another. Next, we have the rest position, which is where the wave starts. The frequency is the number of waves passed in 1 second and is measured in hertz, which is Hz. Displacement is the distance that a certain point in the medium has moved from its rest position, and time period is the time taken for a full cycle of waves to pass. Mechanical waves cause vibrations of particles in solid, liquid, or gas, and should have a medium to travel through. Electromagnetic waves cause oscillations in electrical and magnetic fields. Mechanical waves also travel through matter, for example waves in water, or even talking. Electromagnetic waves travel through vacuum, for example light waves, X-rays, or radio waves. Vacuum is basically no matter or stuff. There are two types of areas in a longitudinal wave. Compressions are areas of high pressure as particles are close together. Rarefactions are areas of low pressure as particles are further away from each other. These waves are often represented using a spring. When you push and pull a string, you can see the compressions moving from left to right, just like energy transferring from left to right. This is also how sound waves move. Sound waves travel through mediums, which is the space where waves can be transmitted. These particles travel fastest through solids as the particles in a solid are more close together than in a gas and more tightly bound than in a liquid. This means that the vibrations are more easily passed from particle to particle. Now we are going to be looking at how we see the pitch and volume in a wave. Well, for starters, what is pitch? Pitch tells us how high or low a sound is, whereas volume tells us how loud or quiet a sound is. Well, to actually see a wave in real life on a screen, you will need an oscilloscope that takes longitudinal sound waves and converts them into transverse electrical signals so that we can see them on a screen. You can actually get a brief understanding of the volume and pitch of a wave by just looking at one. As you know, the amplitude of a wave is half the distance from the crest, the top part of the wave, and the trough, the bottom part of the wave. Well, actually looking at the size of the amplitude can tell you how loud the sound is. The larger the amplitude, the louder the sound. Now, to find out the pitch of a sound. You look at the frequency, which is the number of waves that have passed in 1 second. The greater the frequency, the higher the pitch. So if there were many waves coming in quickly, that sound probably has a high pitch. Waves have time periods, and we can calculate that using this equation. Time period equals 1 divided by the frequency of the wave, where the time period is measured in seconds and the frequency is measured in hertz. Calculate the time period of a wave with a frequency of 75 Hz. So first let's get our equation open and substitute the values as follows. Now we have a calculation, 1 divided by 25, which is 0.04. So the time period of a wave with a frequency of 75 Hz is 0.04 seconds. Let's try another one. Calculate the frequency of a wave with a time period of 0.02. So first, let's get our equation. Now for this question, we will need to find the frequency, which is the given time period to do this. We will have to rearrange the equation into frequency equals 1 divided by the time period so that the f is alone on one side. Now we substitute the values to get 1 divided by 0.02 equals f. 1 divided by 0.02 is 50, so the frequency of the wave with a time period of 0.02 seconds is 50 Hz. What if you didn't have the time period to find the frequency of a wave? Well, this is another way to find out the frequency of a wave. This includes the frequency, wave speed, and the wavelength. There in the equation, frequency equals to wave speed divided by wavelength, or f, which is equal to v divided by lambda. Let's try a question. What is the frequency of a wave that has a wave speed of 60 meters per second and a wavelength of 5 meters? Well, here's our equation. First, we have to substitute the values, which leaves us with f equals to 60 divided by 50, which is 12. So the frequency of the wave is 12 hertz. Another question. What is the wave speed of a wave that has a frequency of 13 hertz and a wavelength of 7 meters? Well, we will have to rearrange the equation to get v, which is the wave speed alone on one side. You would end up with v equals f times lambda. Now we substitute the values to get v equals to 13 multiplied by 7, which is 91 meters per second. If you wanted to find out the wavelength, you would rearrange the equation to get wavelength equals wave speed divided by frequency. Thank you for watching.